The second law of thermodynamics requires us to understand both the entropy change of the surroundings as well as the entropy change of the system. So the entropy change of the surroundings is related to the heat loss by the reaction. So the delta H of the system divided by the temperature. Again, this is usually reported in joules, but delta H enthalpy is often in kilojoules, and so you have to massage the units appropriately. And this is typically in Kelvin. So to report the entropy change of the surroundings, we need to know the enthalpy change of the system. So the delta H for the system is equal to sum of the products minus the reactants. In this case, the delta H is 2 moles of HI. We know that for every 25.9 kilojoules, that's equivalent to 1 mole of HI. That's the delta H of formation for HI right off the table, minus the delta H of reaction for the iodine, hydrogen and the iodine. Hydrogen is 0, the iodine is 62.5, and there's only one, 62.5 kilojoules per mole. It's only 1 mole, allowing us to do the calculation. Negative 10.4 kilojoules per mole of HI for this particular system. This will be the delta H, the enthalpy change of the system. Releases a little bit of heat, a couple kilojoules. Once we have that, we can solve for the delta S of the surroundings. Again, this is in kilojoules, so it's helpful to convert it into joules, because entropies are traditionally reported in joules. This would be equal to, and once we have that number, the temperature is equal to 0 degrees centigrade, which is 273.15 Kelvin, and so we can plug that in. Negative delta H divided by T equals negative times a negative 10500 joules per mole, all divided by 273.15 Kelvin. Gives us the correct units, joules per mole Kelvin. Gives us 38.4 joules per mole Kelvin as our delta S for our surroundings. So from the heat loss, we can figure out the change in entropy for the surroundings. The change in entropy for the system is even more simple. And so the standard entropy of the products minus the standard entropy of the sum of the standard entropies of the products minus the sum of the standard entropies of the reactants will give us delta S for the system. So in this case, delta S of the system is equal to sum of the products, in this case the 2HI, 206.3 joules per mole Kelvin, times the 2 moles of the HI, minus 131 joules per mole of hydrogen, plus the 260.6 joules for the iodine. Gives us a total of positive 21 joules. Gives us positive 21 joules per mole Kelvin for our entropy of our system. So in this case, delta S of the surroundings plus delta S of the system will equal delta S of the universe, which is positive. And in this case, because it is positive, roughly positive 59 joules, we can say that this reaction is spontaneous. Similarly, we can try the same analysis for solid sodium going to liquid sodium at 98 degrees C and see if that is spontaneous. Again, using this idea where we're measuring the entropy change of the surroundings. Delta S of the surroundings is equal to negative delta H over T. We're using at 98, so that's 371 Kelvin is our temperature. And so all we need to figure out is the delta H of the reaction, and from the delta H of the reaction, we can figure out the entropy change of the surroundings and the entropy change of the system and see if these two are spontaneous. So the delta H is products minus reactants. In this case, products, in this case, the liquid sodium has an enthalpy of 2.41 kilojoules minus the reactants, which is 0, so the delta H of this reaction will equal 2.41 kilojoules, positive value. In a similar fashion, we can figure out delta S of the system will equal products minus reactants, 57.56 joules per mole Kelvin minus the reactants, 51.05 joules per mole Kelvin. Says that the entropy change going from between these two is 6.51 kilojoules per mole Kelvin. And so these two values will be useful. Now, what we care about is entropy of the surroundings, delta H of the cis, divided negative delta H of the cis divided by the temperature equal to negative 2.41 kilojoules over 371 Kelvin, 6.49 times 10 to the minus third kilojoules per Kelvin. And then we know that for every 1 kilojoule, that's 1,000 joules, and says that this one is equal to 6.49 joules per mole Kelvin. Very close to this value. So this is almost at the melting point. So these two points are these two values are incredibly close together. So the system plus the surroundings is still a net positive, but barely positive. So this is very, very close to the melting point. So the delta S of the universe in this case is 0.02 joules per mole Kelvin, but still positive, so it's very close to 0. Says that they're almost at the point where the system and the surroundings, the net change is 0. Again, this is the longer way. We don't always have to go all the way to this. We don't always have to find the surroundings. This is where Gibbs free energy comes in.